All right, so today we're going to talk about logarithmic differentiation, and the reason it fits in here is because you need to know how to take the derivatives of logs and exponentials for logarithmic differentiation to work. So, first things first, I want to re-emphasize some of the rules about derivatives. Now, there are two rules about derivatives of things with exponents, all right? So if we have things with exponents, they can happen in two different ways. What am I looking for? My magic pen. We can have a derivative if I have an x to a power. The derivative of x to the n, you bring down the power, reduce it by 1, and x to the n minus 1. When you take the derivative of a to the x, the derivative of a to the x, there we go, is a to the x times ln a. So that's what happens when you have the derivative of a variable base and a constant exponent versus a constant base and a variable exponent. Okay? Now, what happens if you have something that doesn't fall into those categories? If you have something that has a variable base and a variable exponent, well, we don't have a rule for that, so what we do is we take the natural log of both sides, of course, or technically any other log base will do. You may think to yourself, oh my God, why would I introduce logarithms if I don't have to? Except if you're me, you're like, yay, logarithms. So try to be more like me and say, yay, logarithms, because they make everything easier. So let's say we want to take the derivative of x to the 3x. There we go, x to the 3x. And I want to take the derivative. The first thing we do is we take the ln of both sides. So ln y equals ln x to the 3x. Well, the reason we do that is because now this exponent can fall down in front, and I have ln y equals 3x ln x. Now, when I go to take the derivative of both sides, I'm going to do so implicitly. So I'm going to take d dx of both sides. So over here, the derivative of ln y is going to be the derivative of the end over the end. But the derivative of y is technically 1 times dy dx. Now, I'm going to put the dy dx to the side because it makes my life a little bit easier. But you could also write it as dy dx on top right here. But again, you don't have to do it that way. So you can write it as 1 over y dy dx. Then on the right-hand side, I have a product rule. I have the first times the derivative of the second. The derivative of ln x is 1 over x. Plus the second times the derivative of the first. So if I want to solve for dy dx equals y times, well, 3x times 1 over x is just 3 plus 3 ln x. And there's my derivative. Except here's the thing. We were told to take the derivative with respect to x of something in terms of x. So there's usually an implied idea here that we want our answer to be all in terms of x. So our derivative dy dx is y times this stuff. Well, here's the this stuff. But it says y. I don't want to write y. Well, I don't have to write y because look, here's what y is in terms of x. So I'm going to write y as x to the 3x. And my derivative is the original times 3 plus 3 ln x. So logarithmic differentiation is basically a way of giving a process to taking a derivative when you have a variable on the bottom and a variable in the exponent. So let's do it one more time down here. Example 2. I want to take the derivative of 2x to the x squared. If you're feeling good, if you're feeling smart today, take a second, pause the video, and then come back and check it out. But if you're not feeling too confident yet, watch me go through it. So I have d dx of 2x to the x squared. I got a variable base and a variable exponent. So y equals, let's see, 2x to the x squared. I'm going to take the ln of both sides. When I do that, I'm going to bring down the power just to save myself some room. So I have ln y equals ln of 2x to the x squared. I brought the x squared down in front. Now I'm going to take my derivative, d dx. d dx. Derivative over here, the derivative of ln y is the derivative of the end over the end. And then the derivative over here is a product rule. The first times the derivative of the second plus the second times the derivative of the first. So then if I solve for dy dx is y times, well, let's see, these 2's will cancel, that'll cancel with that. So this is really just x plus 2x ln 2x, which, long story short, becomes dy dx equals, what was y? 2x to the x squared times x plus 2x ln 2x.
All right, and last but not least, probably one of the cooler uses of logarithmic differentiation is when you have to differentiate something that's a very giant, complexy-looking fraction. So if you have a giant, complexy-looking fraction and you want to differentiate it, what you want to do here is the first thing we're going to do is we're going to call this y equals the square root of 2x minus 1 squared x plus 3 x squared plus 1. I've got an x to the 7th here. This guy needs to move down, and that needs a parenthesis. Okay. So if I wanted to take the derivative of this, I would have, let's see, a product rule, a chain rule, a quotient rule, a product rule, a chain rule overall. Dear heavens, nope. That's a big bowl of nope, all right? So I have this. Now, if I want to take the derivative, what I can do, because I love logarithms, is I can take the ln of both sides. Why, might you ask? Well, because if I take the log of both sides, or in this case, the natural log, I can use log laws. Yay, log laws. So this thing right here is equal to this thing right here, 2x minus 1 squared, x plus 3, x to the 7th, x squared plus 1, which is also equal to 1/2 2 ln 2x minus 1 plus ln x plus 3 minus ln of x to the 7th, so I'll bring the 7 down in front, minus ln of x squared plus 1. Okay, so then I have this, and now if I want to take the derivative, I can take the derivative of both sides, the derivative of all of that. The derivative of ln y is going to be 1 over y dy dx. The derivative of the end over the end, and since it was a y, I need to leave behind a dy dx. That's an implicit differentiation there. And over here, when I take the derivative, this 1/2 is going to stay. And then these are just different added or subtracted terms, so I can take the derivative one by one. The derivative of this piece is going to be 2 times the derivative of the end over the end, plus this guy, the derivative of the end over the end, minus this guy, 7 times the derivative of the end over the end, this guy, derivative of the end over the end. And then if I want to distribute here, maybe, I don't know, I don't have to, but I might as well. I'm going to have dy dx equals y times, well, if I distribute this 1/2, these cancel, so I have 2 over 2x minus 1. If I distribute the 1/2 to this guy, I have 1 over 2x plus 6. If I distribute the 1/2 to that guy, I have 7 over 2x. Again, this isn't mandatory. Distribute the 1/2 to this guy, I have x over x squared plus 1. And really, I don't like derivatives if they have a y in them when they didn't initially, so I have dy dx equals y, which is the square root of 2x minus 1 squared, x plus 3, x to the 7th, x squared plus 1, times all of this nonsense here. And this, ladies and gentlemen, is the derivative. And you might be thinking, oh, but that's so gross. Well, you have a derivative. Who cares how gross it is? It's a derivative. Leave it alone. Put it in a computer somewhere. Okay? All we really cared about was get the derivative. Did I get the derivative? Well, I hope so. I hope I didn't lose a negative or something. If I lost a negative, somebody let me know. Now, there may be some of you who are like me who might be thinking, but Mrs. Weber, when you bring this 2 down, doesn't it change the domain? Technically it does, because if this is squared initially right here, if I have a squared right here, and then I bring it down in front, now all of a sudden this now has a chance to be negative. So often what they'll do in questions like this is they'll say, let x be greater than 4, or something like that, to eliminate that possibility that your derivative may become negative. In that case, oftentimes with derivatives, we do some simplifying, but off to the side, you might keep track of saying, well, if I bring this 2 down in front, because of this, I now need x to be greater than 1/2 to make sure that I'm taking the ln of a positive value. But again, this is one of those things that you guys don't need to worry about. The AP is never going to try and trick you by switching the domain and asking if you've noticed. And I'm never going to do that either. But if you were doing some complex mathematics in your future, whenever you take these kind of shortcuts for things, you do want to keep track of maybe a change in domain that may have occurred that you didn't quite notice. Okay? All right, so our joke for today is going to be an elephant joke. Why didn't the 2 elephants go swimming? Because between them, they only had 1 pair of trunks. All right, punny jokes, gotta love them. I hope you enjoyed our little log experience. I know I did, because I love logarithms. Have a good day. Bye.